Continuing with section 12.4, this example, we're finding the tangent line at a point on the curve. To find the equation of a tangent line, or actually the equation of any line in space, you need a point and you need a parallel vector. We're going to use that unit tangent vector is a parallel vector, so that's going to help us find the equation of the tangent line in space. So let's find the unit tangent vector. Our vector valued function r of t is equal to 2 cosine ti plus 2 sine tj plus tk. That's a helix. At the point square root of 2 square root of 2 pi over 4. I do want to point out here that in order to determine where the actual time, where the location on the curve is square root of 2, square root of 2, and pi over 4, we need to think about the t, where x is equal to square root of 2, y is equal to square root of 2, and z is equal to pi over 4. In this case, the t can be um, understood to be pi over 4, because the k coefficient is t, and the point in space is, the z is pi over 4. So to find the unit tangent vector, we need to find r prime. The derivative of 2 cosine t is negative 2 sine t. The derivative of 2 sine t is 2 cosine t, and the derivative of t is 1. So you take the derivative of each of the components. That's our r prime of t. You want to take the square root, or the magnitude, of the r prime of t. You square each of the components, add them, take the square root. When you square each of these, you get 4 sine squared t plus 4 cosine squared t plus 1. Using the identity that sine squared t plus cosine squared t is equal to 1, and factoring out the 4, you get that this simplifies to the square root of 5. So the unit tangent vector is your r prime of t divided by the magnitude of r prime of t. So it's 1 over square root of 5 times negative 2 sine ti plus 2 cosine tj plus k. That's our unit tangent vector. At the point, square root of 2, square root of 2, pi over 4, that's your x, y, z, t is equal to pi over 4. So plug in pi over 4 into the unit tangent vector equation and simplify to get the following. 1 over the square root of 5 times a negative square root of 2i plus square root of 2j plus k. That's your unit tangent vector at the time at pi over 4. At the time at pi over 4, the location on the curve is given here, and these are the components of your unit tangent vector. Now we're going to be using the direction numbers negative square root of 2, square root of 2, and 1. That's your parallel vector. Going back, this is our unit tangent vector, then any multiple of this is going to be parallel. So by not using the coefficient here, 1 over square root of 5, you can use the direction numbers, the coefficients of your ijk vectors. So that's going to be your a, b, and c, and using the point given, you can obtain the following parametric equations. X equals x sub 1 plus as, and plugging in the a and the x sub 1, and y equals y sub 1 plus bs, and plugging those in, and z equals z sub 1 plus cs, you get the parametric equations. These are your three equations for the tangent line that is the line that is tangent to the curve at the given point. Now we're using the s here as the parameter instead of our t when this was first introduced, the parametric equations for a line. We use t. Instead, now we're using s because we have a t already used in the definition of the vector valued function. That's our variable t is used there. So to distinguish that, we're using the parameter s. Now again, parametric equations for a line are not unique. You can come up with infinitely many other correct answers for a line that's tangent to the curve in space through the given point. Here's what it looks like graphically. The original vector valued function is this helix. At the point here, you see a line that is tangent to the curve, and the previous parametric equations define that line. For this example, I would like you to find the normal vector and the general normal vector, principal unit normal vector at any time t, and the principal unit normal vector at the time 1 for the curve represented by r of t equals 3ti plus 2t squared j. You can pause the video now and work on your solution for this, and then come back to the video to check your response. All right, to find the principal unit normal vector, you must first find the unit tangent vector. The unit tangent vector is found by taking r prime of t divided by the magnitude of r prime of t. So r prime of t would give you the derivative of 3t is 3, the derivative of 2t squared is 4t. That's our r prime of t, and the magnitude of that would be 9 plus 16t squared, the square root of that. So your unit tangent vector is found by taking r prime divided by its magnitude. So this is our unit tangent vector at any time t. You can plug in 1 to see the actual unit tangent vector at the time equals 1. Now to find the principal unit normal vector, that's that bold N of t vector, you want to find the derivative of your unit tangent vector and divide that by its magnitude. Now this does get to be quite tedious, so you can take the time, double check your work here to find that the unit tangent vector derivative is shown here, and it does simplify with a little bit of algebra. You can simplify to get this. Now you want to take all of this, find the magnitude of that t prime of t vector, find the magnitude of all this, and you get this, and it does simplify to 12 over 9 plus 16t squared. Again, it's a little bit tedious in the simplification. They're using algebra to simplify. And then you take that entire unit tangent vector derivative of that, divide by the magnitude of that derivative, and when you simplify, you get this. So when you plug in t equals 1, the principal unit normal vector is found here 1/5 times the quantity negative 4i plus 3j. So you have your unit tangent vector and your principal unit normal vector. These are going to be 90 degrees. The angle between t of t and n of t is going to be 90 degrees. Those vectors are orthogonal. One is tangent to the graph and one is normal or perpendicular, orthogonal to the graph at the given point. Now you may want to think about that shortcut that I mentioned previously, that the components of the normal vector in the plane are going to be reversed and one of them will be opposite, and that is indeed what happens when you simplify. Okay, the principal unit normal vector can be very difficult to evaluate algebraically. So for those of you that tried that algebraically and did the simplification, you would know firsthand that it can be difficult to evaluate. So you can simplify the algebra by finding the unit tangent vector and observing that that principal unit normal vector, if your unit tangent vector is x of t, y of t, then your principal unit normal vector is reversed. It's either going to be y of ti minus x of tj or negative y of ti plus x of tj. That will always happen if you're finding the tangent vector and the normal vector, the principal unit normal vector and the unit tangent vector in the plane. As long as it's only two-dimensional, you can use this shortcut. But if there is a k component, you cannot use this shortcut. You would have to go through and work it out. So again, referring back to That problem we just did, if the unit tangent vector was 1/5 of 3i plus 4j, then the principal unit normal vector works out to be 1/5 of negative 4i plus 3j. That is certainly a time saver in doing these problems, as long as you have only a plane curve, just two-dimensional.